I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on the AP Physics 1 2024 exam, the FRQs. This is question 3. So today we're going to talk about AP Physics 1 2024 exam, the FRQs, free response question 3, the qualitative quantitative translation question. So in this question, we have a beam that is attached to a hinge at a wall, and it has a string that is attached to the beam, and it gives us some information that the mass of the beam is m, if the hinge exerts a force of FH, and then that theta, that the angle the string makes, is theta 1. And it asks us to draw distinct forces on the beam for the picture on the point in which they are acting. So we're going to draw a force diagram for the place that all of the forces are acting. Well, the first force, we know since it has a mass, there's a gravitational force. So the gravitational force acts from the center of mass, so we're going to draw that from the middle. And the string acts from the far right edge, and it acts at an angle. So we're going to draw the tension force acting at an angle for the tension. Now the hinge also is going to exert a force because it tells us FH, and that hinge force has to balance out the horizontal component of that tension force. We know it has to have a horizontal, so it could also be drawn with an angle as well. So what we're going to do is we're just going to draw the angle of that from the left edge, so the force of the hinge exerts on the left. So this is the force diagram for the beam, where we've got 3 distinct forces drawn with 3 distinct vectors, and each one acting from the point in which it is in contact. And this most likely would be 3 points, one for each force drawn in a correct fashion. The hinge force might only worry about a horizontal component to balance out the tension. It's horizontal component, but that would be the free body diagram for that one. Now the string is now moved to point 2, so theta equals theta 2, so it has a lesser angle. And it tells us that the magnitude of the tension for the dashed line was Ft1, and that the tension in the second position, which the string is attached, is Ft2. And what we're asked to do is compare our answers qualitatively. So we can't derive an equation to explain it. So if you derived an equation, you probably wouldn't get any credit, or you would lose some credit that would have been earned if you didn't use an equation. So qualitative reasoning, we're going to check Ft2 is greater than Ft1. And the reason for this is that the vertical component of tension has to remain constant, and that's to balance out the torque that gravity exerts around that hinge. So when the angle decreases, the vertical component stays the same so that the torques are still balanced, and the tension force has to increase to compensate for the smaller angle. So think of a right triangle where the vertical leg stays the same, but we decrease the angle. Well, what would have to happen if we draw that? That means the hypotenuse is going to have to be much, much longer. So that's the example we have here, with the tension force being the hypotenuse and the vertical component balancing out gravity. The tension force is going to be much greater because that vertical component has to stay the same. Therefore, the tension force would have to increase with a smaller angle value. Now, this one says, starting with Newton's second law for rotation, we want to derive an expression for the tension in the string. And all we want to use is m, theta, and physical constants. So we're allowed to use m, g, and theta. So that means we can't use the force of the hinge. Now it says to start with an equation from your reference book. Now I haven't seen a question like this before where it says to use an equation from your reference book, but we'll discuss that. So the first thing we want to do is we can't use FH, so we're going to place our pivot point at the hinge. Why do we do this? Well, that makes the force that the hinge exerts, its torque is 0 because we're using Newton's second law for rotation, which is torque. So that makes the torque 0 around the hinge if we pick the pivot point at that point. So we can bring in our other forces. The force of gravity points from the center of mass, and the tension force acts from the right edge. Now it just says theta, it doesn't specifically say theta 1 or theta 2, so it doesn't matter the angle that we draw Ft, so we're just going to draw it at some angle theta. Now, using an equation from the reference book, Newton's second law for rotation is that the net torque equals the rotational inertia times the angular acceleration. So I'm assuming this is what they're asking for, starting with this equation, and maybe that's worth a point. I'm not sure. We'll see when the scoring guidelines come out. But the net torque equals I times alpha. Alpha is the angular acceleration. Well, since the beam is in static equilibrium, meaning it's not moving or rotating, that means the angular acceleration is zero. Substituting force of gravity times its distance from the hinge is L divided by 2, and Ft times the length of the rod, which is where Ft acts from, times sine of the angle is the torque that the tension force exerts. So now we're set up to solve our equation for the tension force. We can substitute in mg and add ft sine theta to the other side. Then we can cross out the l's because we have L on each side, and then divide by sine theta, and we get an equation that ft is equal to mg divided by 2 sine theta. So this is the equation for ft for the tension force. Now part D wants to know, is our derived equation in part C consistent with our justification in part B? Well, what we're looking for is an explanation for functional dependence, or how are tension force and theta, how do they relate to each other? So if one goes up, what happens to the other? So in this case, yes, in the equation, as theta decreases, that means that sine theta is going to decrease. But when you divide by a smaller number, mg divided by a smaller number means ft is going to get larger. So that's the functional dependence that we're looking for, is that sine theta is going to decrease. That means tension is going to increase. So yes, my equation backs up my reasoning back in part B without deriving equations. So part E says now the string is cut and the beam begins to rotate. So all we have is the force of gravity acting on it. And it's asking us to draw an angular speed versus time graph. So what we're going to do is we're going to look and see what happens. Gravity is exerting a torque. In this case, this is the greatest that the torque can be because it's perpendicular to the rod. Now, as the rod begins to rotate, what happens to the force of gravity? Well, the force of gravity now has an angle. So it's mg times its distance times sine theta, which means the torque has decreased. And as that continues to rotate, that means the angle is going to get smaller and smaller. So that means the torque is going to get smaller and smaller until the beam becomes vertical. Now, when the beam becomes vertical, that means the torque is zero. But it wants us to draw the graph before the beam becomes vertical. So this is too far of a rotation, so the torque is zero. Now, what's happening is if the torque is decreasing as it rotates down, yes, the rod is speeding up as it goes, but how is it speeding up? Is it a constant rate of change in speed? Well, if the torque is getting smaller, that means the rate of angular acceleration is going to be getting smaller as well. So that means our angular speed is going to increase at a decreasing rate, which means we're going to have a downward opening curve. So we want this curve to be drawn so it's opening up concave down. So the other part of that is we don't want that graph to get completely horizontal. So there's still a little bit of a slope at the very end because that would mean that it got to a vertical position. So we have to stop our graph before that line or that curve becomes completely horizontal to show that it's still reaching the point. It has not yet reached the point of being completely vertical. So this is 2024 FRQ 3, the qualitative quantitative translation. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below and subscribe to my channel, Happy Coaches, and follow me on Instagram and Twitter at Happy Coaches.